Okay, thank you everyone for joining us today. My name is Rogelio Sullivan. I'm the Program Manager at Power America here at NC State University. And thank you for joining us for our monthly technical webinar series, which we hold every first Wednesday of the month at 12 noon. Today's speaker is Dr. Yanjun from Florida State University. He's going to speak on stability analysis and grid disturbance rejection for a 60 kilowatt silicon carbide based filterless grid connected PV inverter. A little bit of background on Dr. Shi. He received his PhD degree in power electronics from Guizhou University of Science and Technology in China in 2012. And now he's a research faculty member at the Center for Advanced Power Systems at Florida State University. Before joining CAPS, he also worked with GE Global Research Center as an on-site contract researcher from 2009 to 2010, and he's been working at the Center for Advanced Power Systems at Florida State since 2014. He's a co-PI of the FSU team to conduct DOE/Power America projects since 2016. His research interests include grid-connected power electronics converters, high-power density PV inverters, high-penetration PV inverters, wide bandgap device application, and control of power electronic converters. And with that, I would like to turn it over to Dr. Shi, but before that, please ask everyone who's logged in to mute yourself if you're not speaking. And when we get to the Q&A period after Dr. Shi is done, I'll ask you to type in your questions into the chat box, which you'll see at the top of your WebEx screen, and then I'll read the questions so everyone hears them, and then Dr. Shi will answer them orally. Okay, Dr. Shi.
Okay, thank you, Rogelio, and thanks everyone for being here. Today I'm going to talk about the filterless grid-tied silicon carbide PV inverter. And first, I'm going to share that why do we want to remove the output filter of a grid-tied PV inverter? And second, I will show a topology and some prototypes we have made, and I will share some issues and two methods that how we solve these issues. And finally, I will show some waveforms that shows the result of those methods. And okay, the first reason we want to get rid of this high order grid interface filter is that because several reasons. We usually call this filter an LCL type filter, but in the real application, sometimes we have to include a damper. It is a resistor that generates loss and heat, and usually this damper will combine with the other RC circuit to bypass some of the low frequency components to make it more efficient. And usually this damper will this LCL filter will also include one or two notch filters to trap the switching frequency. So the structure of this filter can be complicated. And also according to a research from Professor Johan Kohler's group on a 10 kilowatt level three-phase converter, it shows that the loss of the LCL filter and the size of this LCL filter can even be bigger than the converter. So this filter is lossy and takes a lot of size. And for passive components, size usually means cost. And it's also we have this well-known LCL resonance issues. If we do not deal with it carefully, we can end up with resonance. And yes, also because there's some uncertainty from the grid impedance side. So usually it takes a very complicated control method and a lot of design efforts to solve these resonance issues. And the second reason is that when we use a silicon carbide inverter and to increase the switching frequency, we have some new challenges. The first one is the limited CPU time, because when you increase the switching frequency, you want the control frequency also increase this switching frequency. So the time left for you to control this inverter in each interruption will be much smaller. And also, because the whole reason to increase the switching frequency is to reduce the filter value. So when this filter value is reduced, then the uncertainty of the grid impedance will play a bigger role in the whole system. So the stability is more sensitive to the uncertainty of grid impedance, which makes the control of this inverter even harder. These two challenges are actually coupled because we are facing some new challenges, and the resources for us to control it actually become smaller. So our solutions towards this is quite straightforward. We are looking at to completely remove this grid interface filter so that we can have a very simple PR or PRA control, and we can just avoid the filter residence, and also we can save the power loss and weight of the filter. The reason behind this is that is this in three-phase, three-wire system. If you have a three-level topology, supposedly the line-to-line voltage should be 5-level, but in a PV inverter, the neutral of the AC capacitor is usually connected to the neutral of the DC side to bypass the common mode current, so we can have a smaller ground leakage current and a smaller EMI. But this also brings a side effect is that we do not have 5-level. We still have 3-level applied on the grid side, on the inverter side in filters. But if we can increase the output of the inverter to 5-level and remove this capacitor, then we can have a 7-level line-to-line voltage. The right curves, this right waveforms shows that 3-level T-type LCL versus 5-level T-type single L with the same switching frequency. We can see that under the same switching frequency, the bottom curves looks more like sinusoidal. That's the basic idea of this. And if we put this in the numbers, we can see that the 3-level LCL will require a much larger filter value than the 5-level single L. And the 5-level single L requires a small enough inductance that we can actually use the line impedance for the filter. So here is our topology. We have an interleaved boost, and then we use 2 T-type modules, each switched at 50 kilohertz 3-level, and combine those two with an intercell transformer to form a 100 kilohertz 5-level output. So the line-to-line of this inverter is roughly 200 kilohertz equivalent with 7-level. Someone may argue that this intercell transformer is that some sort of the filter. Well, first, the size of the intercell transformer, as I will show later, is quite small. It's much smaller than the conventional LCL filter, and also the power loss is much smaller. And more importantly, because this intercell transformer is designed to be tightly coupled, and so their impedance is only to surprise the high frequency circulating current between these two modules. If we see from the grid side, this equivalent inductance of the ICTs is only the leakage inductance, and in our case, the leakage inductance is less than 10 microhenry. So I think it's safe to say that this is pretty much filterless because the value is so small. And with this topology, we made two prototypes. The first one, we have achieved 60 kilowatt, and with a power density of 3 kilowatt per kilogram. We can see that the ICTs only takes about 9% of the total loss. If we only see the inverter stage, that is about 1/5 of the total loss. And the weight of the ICT is only takes 7% of the total weight. And in the BP2, we increase the power and keep the same size and weight, so the power density became 5 kilowatt per kilogram, and the loss of the ICT is only 8%, and the weight is 13. So we put it to a test. Here shows some standalone waveforms. We directly connect this one to a 100 kilowatt resistive load. There is no extra filters. The cable length is about 1 meter, and we can see that the current ripple is 12%. So supposedly, if we connected this to a grid, the grid has impedance. According to the standards, the short circuit ratio of the grid is no larger than 20, which means we can have a much smaller current ripple than this one. The control structure is shown here. We can see that although there's many control blocks here, but actually this is really simple because there's only an grid impedance standing between the inverter and the grid. We can, looking from the top figure here, we can see that it's a single order system. So we have 4 control blocks here. The first one is the grid current control. The second one is grid voltage feed forward. The third one is the low frequency combo mode voltage compensation. That is we use to limit the low frequency ground leakage current. And the last one is to balance the magnetic flux by controlling the circulating current between the two modules. So if we only see the top two, this is a very simple and straightforward control, just a PR control for a single air inverter. Well, we think this is a simple and straightforward enough. It shouldn't bring us any troubles, right? So that is the most simple structure you can anticipate in a grid-connected converter. Well, it's not quite the case. When we first connect this to the grid, we can see that this thing can work for a couple of seconds, or sometimes even 1 minute. But somehow, at some point, the low frequency harmonic will become very large, and finally it will trip the protection. So we need to figure out what happens. If we model this figure here, we can see indeed this one looks like a single L filter, single L type of inverter. But there's a slightly difference is this S times LG loops. In conventional single L inverter, the voltage sensing part is the grid voltage. But since our case is a filterless inverter, we can only sense the output of this inverter, which is the PCC point. But most of the inductance was contributed by the grid impedance, which means what we are sensing is not the grid voltage anymore. What we are sensing is the combination of the grid voltage and the inverter voltage. If we see the high frequency, this sampled voltage is dominated by the inverter voltage. If we change this control block diagram into its equivalent form, you can see that here we have an actual positive feedback loops caused by this great impedance. That is the reason we have those instability issues. If we write the loop gain of the reference to the output transfer function, we can see that this transfer function can be divided into two parts. The first part in the blue dotted block is a normal single L inverter, and the second part in the red block, this is a new feature that caused by this weak grade effect. And we can see that the loop gain of this GVF is a K, which is LG over the total inductance, which means this value is always smaller than 1. So this positive feedback doesn't necessarily mean this system has to be unstable, but that will affect the stability. If we draw the body plot of this GVF, we can see that what this GVF does is it has a gain, which is not a big issue because we can always to cancel that gain with the controller. More importantly, is it provides a phase lag here at the middle frequency. And we can even derive what is this phase lag cost. We can see that the phase lag is purely caused by K, which means LG over L. And the place where this phase lag happens is caused by K and the delay, total delay in the loop, which tells an interesting story that in silicon carbide inverters, we usually think the delay is not a big issue because the switching frequency is increased, the delay should be smaller. But with this weak grade effect, the phase lag of this delay has been moved to a low frequency domain. We can see that if the LG is 10 times of the leakage inductance, then we have K equal to 0.91. Then we will have this FVF max happens at 0.068 of 1 over TD. That's the effect of the weak grade. So we can also derive the crossover frequency and maximum gain for this loop gain. That we can know that with this K, actually the maximum gain has been reduced, and the crossover frequency has been reduced, which means this weak grade effect together with delay will reduce the bandwidth. Here is an analysis that compares this effect. If we use conventional method with grid voltage feedforward, we can draw this green curve. And if we completely remove the grid voltage feedforward, we have those blue curve. We can see that with the blue curve can have nearly with the same phase margin, the blue ones can have at almost 10 times of the bandwidth. And more importantly, if we see from the disturbance to output point of view, which is an important angle because that will decide the inverter's ability to reject the low frequency grid harmonics, which will finally affect the total harmonic distortion. If we see from this point, we can see that although with grid voltage feedforward, we can have some noise suppression at the low frequency, but in the middle frequency between this 23 Hertz and 1.2 kilohertz, we kind of have an effect that can amplify the noise, amplify the disturbance from the grid, which is not a good thing. So our method, the first one is quite straightforward. We just remove the grid voltage feed forward. Some people may think that this can bring some issues, right? In most all the grid connected impedance, we have to have grid voltage feed forward to compensate for the harmonics, to know what the grid voltage is. So we keep the fundamental frequency, and the method we use is the byproduct of the PIL algorithm, because in a conventional DQ-based PIL, we can lock the VQ equal to 0, so we are in phase with the grid. Then we are left with VD. If we put a moving average filter on VD, we can get the DC part of VD. And if we convert it back, then we can have a pure sinusoidal 60 Hertz voltage that is equal to the fundamental of the grid voltage. The reason we use this moving average filter is that the control complexity of this MAF is not relevant to the data point, or it's not relevant to how powerful this filter is. If we want more filtering, if we want to get rid of more harmonics, we just increase the size of the filter, but that doesn't affect how many CPU cycles it takes. It always takes it always takes 5 extra CPU cycles. With this method, we can remove the effect of the grid voltage feed forward with only 5 CPU cycles. So here is a comparison of the what we call the fundamental frequency grid voltage feed forward versus the conventional instantaneous grid voltage feed forward. We can see that with different delays and with different LG over L leak ratio, we can have different closed loop bandwidth. But in general, this FFGVF has a much larger bandwidth than IGVF. If we zoom those curves, we can see that with IGVF, the closed loop bandwidth is very sensitive to the delay and to the weak grid effect. One thing we should notice that the delay here are not big numbers, right? If we switch at 50 kilohertz, then with the zero-ish delay and with the bridge delay, we will have a roughly 30 microseconds delay, which gives us these orange curves here. Means that if the grid impedance is 10 times of our inverter leakage impedance, then the bandwidth here is less than 500, which is not a big value even for silicon-based inverters. But with FFGVF, we can see that first, the bandwidth is not affected by the weak grid effect. Second, with increased delay, the bandwidth will reduce some. But even with 100 microseconds delay, we can still have a decent bandwidth at over 1K hertz. But as we mentioned, that the grid voltage feed forward has its benefits. So our second thought is to keep some part of the grid voltage feed forward by just place a low-pass filter after the voltage sensor. And if we go back to see our control block, we can see that after this voltage sensor, we already have a low-pass filter in the signal path. This is this is because this environment always have noise. To get rid of the noise, we usually have a low-pass filter in the signal conditioning circuit to get rid of the switching noise or higher noise. So in this method, what we need to do is to modify the RC parameters after this on the signal filter after the sensor. And these equations gives the cutover frequency of this filter, and for the simplicity, we only require the first order filter. So the FFGVF can implement a pure bi-analog filter in the signal path, so it costs 0 CPU cycles. And if we write the control block diagram of this method, we can see that the effect of this FFGVF is not to reduce the delay. It is rather to add more delays in the system, so it can move the effect area of the delay to even lower frequency, while we already have enough phase margin. If we put these three methods into comparison, we can see that the FFGVF and FLGVF have the same crossover, have the same bandwidth. If we think from the disturbance to output point of view, we can see that the FFGVF has the effect of the IGVF and the FFGVF. It has a similar attenuation in the middle frequency range as FFGVF, but it's also provided the extra attenuation at the low frequency. We can think that if we draw the low frequency equivalent circuit of those three methods, we can know that the FFGVF works as a second order RLC filter, while the other either works as an undamped LC filter or works as a first order RL filter. And here is how we test this method. We connect our inverter to a 1.5 megawatt transformer with around 35 meters of cable, because this transformer is in the next room, and we measure the total grid inductance use current ripples. It's roughly 120 microhenry. So this is the experiment result of FFGVF. It shows that the inverter can work. It has sinusoidal waveform, and the grid current THD is 3.54. And if we test our FLGVF, we can see that the THD becomes much smaller than the FFGVF, because the low frequency harmonic has been suppressed. I'm not quite satisfied with the high frequency ones, because in our case, with some EMI noise coupled into the control circuit, we actually have to add more EMI noise filters in the digital EMI noise filters in the controller, so that caused some delays. That affects our performance at a higher frequency. And here is a startup waveform with FLGVF. It has a smooth startup. So to conclude today's presentation, we know that with silicon carbide device and multi-level topology, it is possible to remove the output filter, to remove the LCL filter from a grid-tied PV inverter. And controlling a filterless inverter is rather simple. It's similar like controlling a single L inverter. So no dampings, no impedance shapings will be needed. We can just use PR or PI controller. And we have two methods. the first method is quite straightforward. It can solve the issues, but it has limited rejection against the great voltage disturbance. And the second method can suppress the great disturbance. And if we can have a faster controller, if we can make the delay smaller, then the FFGVF will have more effect. Here is some related publications about today's topic, and thank you all.
Thank you very much, Dr. Shi. That was a very good presentation and very informative. We really appreciate it. Are there any questions for Dr. Shi? There are not too many people online, so actually you can just speak out instead of using the chat box as I suggested earlier.
Hi, Dr. Shi. This is Yanjun from Wolfspeed. So you got rid of the capacitor, right?
Yes.
So is there any increase for the inductor?
Actually, we also get rid of all the inductors. That's why we call it a filterless inverter. That's if we can see from this topology here. We do have a this inverter is actually green impedance. We are using the line impedance for the filtering. And those three intercell transformers are highly coupled magnetics that doesn't work as a filter. It's like a wave commander to combine 2 3-level waves into a 5-level waveform. And the weight of the ICT is 500 grams. It's 0.5 kilogram.
Mm-hmm. So you totally got rid of the ALC filter?
Yes, yes.
Okay.
Are there any other questions?
Yes, I have a follow-up question. This is John Wenxiao from Wolfspeed as well. If you totally get rid of the filter, how about the EMI filter? Do you still need to add the high-frequency EMI filter in between grid and the inverter?
Yes. That is a great question because that is what we are working on. Usually in PV inverters, not every customer requires a EMI filter, but we think it's better to have EMI filters because this is silicon carbide inverter, right? So we are designing EMI filters right now, and our main point of this EMI filter is that make the cutoff frequency of the EMI filter quite high. We are actually use some notch technology and some canceling technologies to make the resonant point of this EMI filter much higher than the control frequency. So from the control point of view, there is no resonant, there is no filter. But that EMI filter only works for the EMI.
Okay, thank you.
Are there any more questions for Dr. Shi?
So how about the load response?
I do have a step-up waveform somewhere. Let me dig out. Here is a limited command startup. Maybe I can find a step-up waveform with a step command. Let me dig out some waveforms. Okay, here the figure 27. This is the we convert the three-phase stack waveform into D-axis. So we can see here that it's quite fast. The blue one is the mirrored waveform. I don't know if you can see this clearly.
Okay. So how about the voltage? Is there any distortion when you apply this load?
Because we are connected to the grid, right? So the voltage is if you are asking if we connected to a standalone load, then there's no distortion. We can see from the feature here. Okay, here is we connected to a load. The top ones are the voltage. Yeah.
Okay.
Yeah.
It's pretty good.
Okay, any more questions? If not, then thank you very much again, Dr. Shi. I really appreciate it. That was a very good webinar. Can you please send me a copy of your presentation with any information that you don't want shared, and then I can respond and send it out to anybody who requests it rather than just blast it out to the entire world.
Okay, okay.
All right, thanks very much.
Thank you.
Thank you.
Thank
You're
you.
welcome. Thank you all very much for joining us, and hopefully we'll see you again on Wednesday, Wednesday, December 6th at 12 p.m.